In the previous module, we have discussed some properties of connected spaces and disconnected spaces. We have provided some examples of disconnected spaces. For example, the set of real numbers deleted 0. For example, set of rational numbers. For example, set of all irrational numbers. These are disconnected spaces. Also, the Sargent-Frey line, that is R with lower limit topology, is disconnected because every semi-open interval, that is left hand side is closed and right hand side is open, this kind of semi-open intervals are both open and closed sets in the Sargent-Frey topology. So, they are also gives a separation of the Sargent-Frey line. But we have not provided any example of connected topological spaces. In fact, if we can prove that R is a connected topological spaces, then we will be able to prove that every Euclidean space is connected. So, in our next module, our main target will be to prove that R with usual topology is connected topological spaces, and hence using this we shall prove the intermediate value theorem. What we have done in the previous module gives us a number of ways to build new connected spaces from old one. But as I have told that still now we have not provided any example of connected spaces. Our first example of connected space will be the set of real number with usual topology. In fact, we shall prove that the following theorem: a non-empty subset of R is connected if and only if it is an interval. An immediate consequence of this theorem is the following generalization of intermediate value theorem. Suppose X is a connected topological space and f is a continuous real valued function on X. If PQ belongs to capital X, then f takes on all values between Fp and Fq. We shall prove that assuming that R is connected. In fact, any subset of R is connected if and only if that is an interval. So, let Bx is a connected topological space and f is a continuous real valued function on X and PQ belongs to capital X. Since continuous image of any connected topological space is connected, therefore f of capital X is connected subset of R. Hence, f of capital X will be an interval, as connected subsets of R are precisely intervals. Now, as PQ belongs to capital X, therefore Fp and Fq both belongs to f of capital X. Now, since f of capital X is connected, therefore any value in between Fp and Fq will be attained by f on X. Hence, we have the generalization of intermediate value theorem. Now, let us come to the proof of the fact that connected subsets of R are precisely intervals. Let us first assume that J subset of R is an interval. We know that characteristic property of being an interval is that if xy belongs to that set, then any point lying between x and y will be contained in that set. Now, if J is not connected, there are non-empty disjoint open subsets, say U and V of R, which separate J. That means J will be contained in U union V, and both J intersection U is non-empty and J intersection V is non-empty. Let us choose A in U intersection V and B in V intersection J, and assume that A less than B. In fact, we can do this without loss of generality because we can change the role of U and V if necessary. Now, since J is an interval and A and B both belongs to J, therefore, closed interval AB is contained in J. Since U and V are both open subset of R, there exists some epsilon greater than 0 such that A to A plus epsilon is contained in U intersection J and B minus epsilon to B is contained in V intersection J. Let C is equal to supremum of U intersection closed interval AB. By our choice of epsilon, A plus epsilon less or equal to C less or equal to B minus epsilon. In particular, C is between A and B, so C belongs to J is contained in U union capital V. But if C is in U, it would have a neighborhood C minus delta to C plus delta is contained in U, which would contradict the definition of C. Similarly, if C belongs to V, then we also get a contradiction. Therefore, J is connected. So, we have proved that every subset of R which is an interval is connected. The converse part is easy. Assume that J is not an interval. That means there exists some A, B belongs to J and some C in R greater than A, less than B, and C is not contained in J. Then the set of all real numbers less than C and set of all real numbers greater than C make a separation of J because J is contained in their union and both of them meet J non-trivially. So J is connected. Let us prove another result in connection with cardinality. Let X be a connected normal space which is also Hausdorff space and which contains at least 2 points x and y. Then there exists a continuous surjection f from x to 0 1. In particular, x is uncountable. To prove this, let us choose two distinct points x and y in capital X. Now, since capital X is normal, therefore, by Eurytion's lemma, there exists a continuous function f from capital X to the closed interval 0 1 such that f of small x is equal to 0 and f of small y is equal to 1. Now, since capital X is connected, f of capital X will also be connected as continuous image of any connected space is connected. Therefore, we have that f of capital X is an interval since only connected subsets of R are intervals. Therefore, the whole closed unit interval 0 1 is contained in f of capital X. Hence, f is a continuous surjection from x to closed interval 0 1. This also proves that capital X is uncountable because image of any countable set cannot be uncountable. So, in the previous module we have given examples of some disconnected topological spaces, and in this module, in the previous disconnection, we have provided our first example as a connected topological space as our Euclidean space R, and any interval is connected. This will help us to provide rich source of connected topological spaces. In fact, most of the examples of connected topological spaces will be created by using the connectivity of R. So, our first observation is that any Euclidean space is connected because we have already proved that finite product of connected space is connected and R is connected. So, Rn is connected for any n. Since any open disk in R2 is homeomorphic to R2, so is connected. Any rectangle being the product of two intervals is also connected because connected subsets of R are intervals. Since S1 is a continuous image of R by the mapping P of x is equal to e to the power 2 pi I x, when S1 is considered as the unit circle in complex plane, we have that S1 is connected. Now, we prove that there must exist a point x in S1 such that f of x will be f of minus x for any continuous map from S1 to R. For this, let us consider a map Gx is equal to fx minus f of minus x. Then G is continuous mapping. Now since G from S1 to R is continuous, therefore G of S1 must be connected and therefore will be an interval. Now since Gx is equal to fx minus f of minus x, therefore there must exist two points, say A and B in S1 such that G of A is positive and G of B negative. But both G of A and G of B are contained in the interval G of S1. That means that 0 is contained in the interval G of S1, which further implies that there exists some point x belongs to S1 such that G of x is equal to 0. That is, f of x is equal to f of minus x. This complete the example. Let us consider another example. If f from closed interval 0,1 to closed interval 0,1 is a continuous map, then there exists a point x belongs to 0,1 such that fx is equal to x. It can be proved that by considering a mapping Gx is equal to fx minus x. Let us keep it as an exercise. Let us consider few more examples. As an application of connectivity of intervals of R, we can prove that an open interval and closed interval are not homeomorphic. In fact, if possible, let 0,1 open interval and closed interval 0,1 are homeomorphic. Then there exists a homeomorphism f from the closed interval 0,1 to the open interval 0,1. Then f of 0 will be contained in the open interval 0,1. Now if we delete the point f of 0 from the open interval 0,1, then this becomes disconnected because this does not remain an interval. But if we delete 0 from the closed interval 0,1, then it remains connected because it is still an intervals. Now if we restrict f on the semi-open interval 0,1, then f from semi-open interval 0,1 to the open interval 0,1 deleted the point f of 0 is a homeomorphism, which gives a contradiction because the right hand side is connected and left hand side is not connected. Therefore, open interval 0,1 and closed interval 0,1 are not homeomorphic. Similarly, we can prove that open interval 0,1 and semi-open interval 0, 1 are not homeomorphic. The following example shows that any Rn is not homeomorphic to R for any n greater or equal to 2. The technique is same as the previous example. In fact, if we remove a point from Rn for n greater or equal to 2, then it still remain connected, which will be proved in the next module when we will study the path connectedness. But if one point is removed from R, then it becomes disconnected. Now, let us prove another product theorem about connectivity. We have proved that finite product of connected spaces is connected. In the following theorem, we shall prove that countable product of R is connected. To prove this, in fact, we shall use the technique of the fact that finite product of connected spaces is connected and combine this with the result that closure of connected space is connected. Let us set for each n belongs to capital N, Rn hat is equal to all those sequence of real numbers such that xi is equal to 0 for all I greater or equal to n. Then clearly Rn hat is homeomorphic to Rn for each n and hence connected. Now observe that for each n greater or equal to 1, Rn hat contains R1 hat. Therefore, if we take the union of Rn hat as R to the power infinity, then it becomes a connected space. Now, to prove the result, it is sufficient to show that the closure of R infinity is equal to R omega. So, now let U be a basic open set of R omega. That means U is equal to product of Ui, where only finitely many Ui may be proper open set and except finally all Ui are whole R. Now let capital N be the largest positive integer such that Ui not equal to R. Then it is clear that U is equal to Ui product that meets R capital N hat. Therefore, R infinity is dense in R omega and hence R omega being closure of the connected space of R infinity is connected. Let us end this module with the introduction of totally disconnected space. We have already proved that RL is disconnected. In fact, we have already told that semi-open interval 0, 1 is both open and closed set in RL. In fact, any semi-open interval is open and closed set is RL. This example leads us to the following notion. A space X is called totally disconnected if its only connected subspace are one-point X sets. Clearly, if X has the discrete topology, then capital X is totally disconnected. But there are totally disconnected spaces which are not discrete. For example, RL is an example of totally disconnected space. The set of rational numbers, the set of irrational numbers, the set of all periodic numbers, Cantor sets are all example of totally disconnected spaces. So, in this module, we have provided our first example of connected space as R and uses it to prove that every Euclidean space is connected. In our next module, we will go for further examples. With this, we end this module. Let us pass to the next module.